everyone, tonight we're going to be going over Module 3, Chapter 4, Number Theory, and Chapter 5, which is Integers. And I will be going over it with you, and I am Katie Hardister. So here is our first equation, using the divisibility test to decide which of the numbers are divisors of the numbers in the left column. So what that is asking is these are going to be our divisors here. So 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So each divisor has a rule. So the rules for each divisor are 2, it ends in an even digit. 3, the sum of all digits is divisible by 3, so on and so forth. So let's just jump right in, and I did go ahead and work these so that we could maybe more talk about these equations. If we were in an actual classroom setting, then we would of course have the students work independently on these, and then I would of course maybe scan the room, walk through with students, and then we would work through some of them together. So jumping right in, we see that 684, 2 would be a divisor for it because the last digit, it ends with 4. So we don't even have to look at the rest of the number. We can just look at the last number. So 4, yes, it is divisible by 2. Again, 4, yes, is divisible by 2. What about 1? 1, of course, is not divisible by 2, so we would just put no. 0 would be considered an even number, so yes. Again, 0 is an even number, so yes. And then 8 is, of course, a divisor of 2. Or 2 is a divisor of 8, rather. Moving on, the sum of all digits is divisible by 3. So what that's saying is we want to add 6 plus 8 plus 4 would be 18. So is 18 divisible by 3? Yes, it is. So moving along, we're going to do the same thing. Just add 2 plus 0 plus 6 plus 4 is 12. So yes, 12 is divisible by 3. Again, 12 is divisible by 3. The sum of all of these numbers here is 27, so yes. Here's one. The sum of this number here is 32. 32 is not divisible by 3. And then so on and so forth. The sum here of these digits is 27, and it is divisible by 3, so we'd of course put yes. So this rule for number 4 is the last 2 digits are divisible by 4. So what that is saying is not 84. It's not asking is 84 divisible by 4. It's saying is 8 divisible by 4? Yes, it is. And then is 4 divisible by 4? So it's asking as if each number, each number has its separate own number. So is 6 divisible by 4? No, it's not. Is 4 divisible by 4? Yes, it is. But the fact that 6 is not divisible means that no, the entire equation would not be divisible by 4. Moving on, 5 is not divisible by 4, and so is 1, it is not divisible by 4. Now you may think, well, we can take 4 out of 5, right? But it's not a divisible by a whole number. So we'll see that as a reoccurring theme here in this presentation, that we want, when we say is something divisible by something, we're asking is it divisible as a whole number. So moving on, for 5, the rule for 5 is if it ends in a 0 or a 5, then it's divisible. So again, all we have to do is just look at the very end number. So we see that 4 is not 0 or 5, so it would be no. Again, 4 is not 0 or 5, so no. Here's one that ends in 0, so yes, it would be divisible by 5. Again, this one ends in 0, so it's divisible. And then 8. Again, we could take 5 out of 8, but it wouldn't be a whole number, would not be our solution to the equation. So that's not what we're looking for today. So the rule for 6 is if it is divisible by 2 and 3, So we see that 684 is divisible by 2 and 3. So that would be yes. And we would just go down the line and see. So the rule for 7 is kind of tricky, and it involves a couple of steps. So what we're going to do is we're going to take off the last number. So we see 4. So we're going to take 4 off, and we're going to double that number. So then we're going to say it's 8, and then we're going to subtract that number. And then we say, is that number divisible by 7? So the answer here would be 60, and no, that is not divisible by 7. And then we'd go on and so forth. See, the numbers get kind of large, so this would be very useful to have a calculator or scratch paper to work these problems. So are the last 3 digits divisible by 7? Now, whenever we say the last 3 digits, what if the equation, or what if the number is only 3 digits? Well, then it's just those 3 digits. So 684 is not divisible by 7. So 0, 64, same thing. I went ahead and carried the 0 to just show, but it's the same thing as saying 64, because if 0 is in front of a number, then of course it's just, we could take it off. So 64 is divisible by 7. 51 is not, whereas 490 is not. 740 is not, and 526 is. So here we see the sum of all of the digits is divisible by 9. So if we add 6 plus 8 plus 4, it equals 18. 18 is divisible by 9. And then again, we're just going to go through here and find if it is. So again, another easy one. 10, the rule for 10 is if it ends in 0. Easy peasy. We've seen something very similar to this here before. You can actually see that our number, or that our yeses and nos are the same, identical to 5. So no, 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 yes, yes, and no. 11 gets a little tricky again as well. We see the alternate adding and subtracting digits and number. The answer is 0. We're going to alternate adding and subtracting the digits and the number, and then if the answer is 0 or 11. So then I have that worked out here for us, and we can see that there. So again, if we were in a normal classroom setting, then we would of course work these together a little bit more in depth. Moving along though, we're going to see here the thing, it's called the process of nines. We could also call this the casting of nines. We can call them the casting of nines because what we're actually going to do is cast out the nines. So what that means is we're just going to take, for instance, 416 does not have a 9 in the equation. So there's nothing to cast out. So what we're going to do is we're going to get the sum of this number. So we're going to say 4 plus 1 plus 6 equals 11. But we want to have a single digit number when we're done. So I can say 1 plus 1 equals 2. And then what about here? So I see, let's go ahead and change our pen here. So I see 7 plus 4 plus 9. Now we don't need 9 because we're casting it out. So let's just cross that out so that we don't confuse ourselves. And then again, we don't have to cross out 0, but like we said previously, 0 doesn't really count in this equation. I mean, any number plus 0 would just be the number itself. So let's just go ahead and cross that out. So we do 7 plus 4 is 18. 18, what did I do here? Oh, it's not 8. 7, 8, 9, 10, 11. I just typed that wrong, no problem. So let's change that to 11. So 11, again, we want to have a single digit number. So 1 plus 1, again, is 2. So then we can take here, and again, we're going to cast out that 9 here. And then we're going to say 6 plus 8 plus 4 plus 4 is 22. 2 plus 2 is 4. So then we can say here, all we're doing is we're taking these numbers here. 2 plus 2 plus 4, and you see that I have that typed here, equals 8. And then what we did here is, go back. We can see that these numbers here, 8 and 2, are not the same. So we're just going to write that they are not a match. All right, and then moving right along. So again, same concept, here we go. We're just going to briefly go over this here. We see that there's no 9, so we add each of those numbers together. We went ahead and carried that 0 just to keep everyone straight. And then we say that the sum of this number here is 18. 1 plus 8 is 9. Now we think, wait, hold on. We can't have 9 because we're casting out the 9s. In this case, because we added those numbers together, we can carry the 9. So we're going to say 9, and then continuing 6 plus 8 plus 8 plus 8 is 30, 3 plus 0 is 3, and then we say 9 plus 5 equals 5. Because we're going to take that out there. So what we did was we added those numbers together. So just 5 would be our answer there. And then 6 plus 0 plus 2 equals 8. So then we're going to add those together. 7 would be our solution here, and 6. So again, we're going to say that it is not a match. All right, and then another one. So looking at this, we can actually see that it's a subtraction equation. So that's okay. Still going to handle it the same. We see that it's 7. The reason that we did this is because those added together is an 8. So we just took that out. So 7 plus 7 plus 2, 17. 17, or 1 plus 7 is 8. 7 plus 4 equals 11. Again, 1 plus 1 equals 2. So we're just going to add those together. 8 plus 2 is 10. And then we're going to add the actual answer that they said we got here, and that equals 5. So we're actually just off by a tens place. So the actual answer to this equation would be this here, 74,688. They were just off by 10. So this is a great tool to just check ourselves. You can say, well, why don't we just put this in the calculator? Well, we don't want to put it in the calculator because this actually challenges us, but yes, it is quicker to just use a calculator. Here is multiplication. Again, it's just going to be the same exact thing. 3 plus 3 plus 7 is 13. 1 and 3 is 4. 4 plus 8 is 12. 1 and 2 is 3. 3 plus 4. And then again, we're just going to cross out those zeros, cast out the 9s, and we say 2 plus 4 equals 6. Here we have what we're going to do is we want to look at this here. This is going to be our diagram that we're going to use to solve a couple equations here. So first we want to know what, show the rods which will measure out to 9. So we see here that if we take rod 1 and 8, that will equal 9. Isn't 1 and 8 the same thing as saying 9? 1 plus 8 equals 9. 7, so if we take 7 here, and 2, 7 and 2 is again 9. So really all we're doing, wouldn't you argue, is that we're just finding the greatest common divisors in this, or the factors rather. So again, we want to take a look and see, show which rods will measure the sixth rod. So here we see that we have 1 and 5. So 1 plus 5 is 6. 2 and 4 is 6, and 3 and 3 is 6. So use parts A and B to show the greatest common divisor of 9 and 6. So looking at this, you know, a lot of us could just do this in our head. This was just a example though. So yes, it is easy to say the common divisor of, or the greatest common divisor of 9 and 6 is 3. But once we get into more complex problems, you know, it would be good to know how to work these out. So moving along, we can see that if we made an 18 train, what rods would make it up? So we know 10 and 8. So 10 and 8 are factors. 9 and 9 are factors of 18. 6 and 6 are factors of 18. And then we can see here 3 plus 3 plus 3. 3, 3, and 3 are factors of 18. And then all of these 2's here and 2 are also factors of 18. Now, you may be thinking, well, what's an easier way? Because looking at those gets kind of confusing. For me personally, I like to see graphs. I like to see things that make sense. So here, let's see, how could we use these blocks to demonstrate GCD, which is greatest common divisor. So we see that 2, 2, 2, 2, 2, and 2 is a factor of 12. So this is the same thing. You may have seen this before. I could do, if I do this here, 2 plus 2 plus 2. So 4, 4, and 4. So what is 4 and 4? 4 and 4 is 8. Let's carry this 4 up. 4 and 8 equals 12. So this is very similar here to what is called a factor tree. That's just another way. All this is a factor tree, just broken down into a graph form. So I can do that, and I could go through each of these, and we could see that each of these numbers are factors of 12, including 6 and 6, 4 and 4, and 4, 3, 3, 3, and 3. And then we can do the same thing, same exact thing that I did here. I'm not going to, because I think that we kind of get the gist, but of 18. So our 2's here, our 3's, 1, 2, 3, 4, 5, 6 3's, 3 6's, and 2 9's. Now, what we are trying to do is find the greatest common divisor of 12 and 18. So do we see anything that is common between 12 and 18? Because I would argue that 6 and 6 and 6, 6, and 6 are the same here. So I would say that the greatest common divisor of 12 and 18 is 6. So moving right along here, what we're going to do here is deal with the least common multiple. So the least common multiple is the smallest. What we're trying to do is find the smallest number of all of the numbers that can divide into. So we're trying to see, what can 75 divide into? Like, what's the smallest number that we can divide into? So setting this up, and I'm looking on my notes here. So they give us here our numbers, okay? And these are the numbers that we're trying to find. So I did already go ahead and work this one out so that we could talk about it together. So the first thing that we're going to do is actually put these numbers in here. And then what we're going to do from there is we're going to take a look, and we would want to factor out any prime divisor divisor and replace it with prime numbers. So that's all we did here. And then what we'd end up doing is taking these numbers here and this little L shape or arrow shape, and we're going to add those together. Okay? So what we did is we continued into the last row. So this would be the last row and column here, is that it contains only distinct prime numbers and ones. So here we can take a look and we can see that we have 2 times 3 times 2 times 5 times 5 times 2 times 1 times 7 equals. So this is kind of confusing to me to look at, and it's kind of a mess. So what we can do is we can actually kind of collect like terms. So what we're going to do, and whenever we write this, we want to write it in what's called descending order. So that means that we're going to take, you know, let's see, we have 1, 2, 3 twos. Okay, so the way that we would write that, instead of saying 2 times 2 times 2 times 2, is we could actually write 2 with an exponent of 3. This tells me that there's 3 2's in this equation, times the next one that I see is 5. So I have 5 with an exponent of 2. So that tells me that there's 2 5's, times 3. Once we get into everything has an exponent. These all have an understood 1 here. So I'm just clicking. These all have an understood 1. So just continuing, we don't have to write the 1 though, because it's understood. So times 1 times 7. So this right here is the same thing as that. It's just in a little bit of a prettier form, if you will. So what this would be called here is the prime power form. Okay, so after we get the prime power form, what we're going to do from there is actually do the equation. So you can type this into your calculator or you can do it by hand. Either way, you're going to get this number here, which is 4,200. 4,200 is the, I am writing the wrong thing, I tell you. We're not working on greatest, we're working on least. 4,200 is the least common multiple of 75, 24, 30, 41. And that is how you would write that. I did include on the ones that we needed a little key or cheat sheet of our prime numbers, because I know we're just kind of learning those. So moving right along, looking at our next one here again, I have it worked. If we were in a classroom, we'd work it together, but that's okay. So again, we're wanting to find the least common multiple of 48, 25, and 65. Put those numbers here. And then we solved down to finding these numbers here, which are the lowest prime numbers that we can get them to, the most distinct prime numbers down to ones. So just moving right along, we can say 2 times 2 times 2 times 2 times 5 times 3 times 5 times 13. Or we can say 2 to the 4th power times 3 times 5 to the 2nd power times 13, which is 15,600. Moving right along, same thing as we did before. So the least common multiple of 40, 12, 44, 363. is 14,520. Again, all we did here is we took and, where is my pen? All we did here is just took the numbers that we were wanting to find the least common multiple of, put them in here, and then we put here, we got this down to the least, we put it to the most distinct prime numbers, or down to ones. Again, same thing. These are the numbers that we're wanting to find the least common multiple of. These are the simplest prime numbers, distinct numbers that we can get them to down here in this row and this column. I'm sorry, this column and this row. And then from there we would just of course multiply, and this is our least common multiple. So here we're going to do an equation, and we're wanting to demonstrate how many more revolutions the small gear, so the small gear being this one here, the 48 teeth versus the 84 teeth. The small blue gear we'll have to make before A and B are in the same position again. So what we're wanting to do here is find the least common multiple of both gears. So I did go ahead and put out the factors of this, and we see that the least common multiple of 48 and 84 are 336. So what we want to do here is we want to divide 336 by 48. The reason that we're doing this is because that's the least common multiple, and we're going to divide it. Now that's the least common multiple of 84 as well as 48, so we divide it by 48, and that gives us 7 rounds. What that tells us is that this little gear here would have to go around 7 times. We would have to rotate against each other 7 times before we were back, before A gear and B gear are back in the same position. So that would be 7 rounds would be the answer to our equation here. So here we are on our magic square, which is a lot of fun. And our magic square, what we're going to do here is we are going to, first we need to find out how we even need to set this up. So how do I know how to set it up? What we're going to do is we're going to add each of these numbers together. So -7, -6, -5, -4, -3, -2, -1, 0, and 1 together. That gives us, let's see, let's write it here, -27. And then we can say -27 divided by 3 is 9. So it's safe to say this works here, so let's just go with that one. We can say that our magic sum is 9. So let's keep that rule in mind. I like to start in the middle. Whenever we got this equation, we did get the numbers here, 0 and 1. So let's just pretend like, you know, those aren't there. What we do though, whenever we put a number in, what I personally do, because it helps me keep track and not get confused, is I go ahead and cross them out. So let's go ahead and cross 0 and 1. Now you may be thinking, how do I know which number goes in the middle? Simple, easy peasy. We know that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. 9, that means that -3 would be in the middle. So if I know that -3 is in the middle, I have 1, 2, 3, 4, and 1, 2, 3, 4. So let's go ahead and write -3 right there in the middle. From there, all we have to do, we already have 0, so let's just plug in some numbers and see. Now remember, we want this to add to 9, so let's say -7 if I can write, negative 7, where'd my negative go? Negative 7 and negative 2. That would equal 7, 8, 9. A positive plus negative plus a negative makes a positive, so that would equal 9. We know that 7 and 3 and negative 7, negative 3, and 1 would equal 9. So that's one row and one column done. What number could I add together now? Maybe let's say 5, negative 3, and negative 1 would equal 9. And then negative 4, 1, and negative 6. So what we did here is whenever we have our magic square, now we can check ourselves. With checking ourselves, what we're checking is that if our magic sum is 9, we want, whenever we say our this row here, the sum of this, so sum is adding, has to equal 9. So every single way that we go, it has to equal 9. And if it does, then that is our magic square. If not, then the equation just might not be solvable, or we might have a number in wrong. So with that being said, I think that concludes our presentation.